Okay, so we're starting geometry now. First couple of questions are basically review questions. You're supposed to fill in the blanks. So problem number 1 says the sum of the measure of two complementary angles is something degrees. Well, a complementary angle, by its definition, complementary angles add to 90 degrees. So here we have a right angle, and we have some angle theta 1 and some angle theta 2. And again, by definition, these two have to add up to 90 degrees, the values. So the answer is 90 degrees. Problem number 2 is the sum of the measure of two supplementary angles is blank. Sorry, swallowed something that I shouldn't have swallowed because I'm eating my lunch. Okay, so supplementary angles, again by their definition, add up to 180 degrees, and a 180 degree angle is a straight line. So if we were to represent these two angles as theta 1 and theta 2, then by its definition, the two angles add up to 180 degrees. So the answer is 180 degrees. Problem number 3, the measures of two vertical angles are equal or not equal. Well, the vertical angles happen when you have two intersecting lines. And so this angle would be theta, and this angle also would be theta. Now if you look at these other two angles, call this theta prime and this one theta prime, these are also equal to each other. And we can also say that theta plus theta prime is equal to 180 degrees, because this is a straight line, so this is 180 degrees, so each one of those adds up. So the answer is equal, that vertical angles are equal to each other. And the measures of blank right angles add up to the measure of a straight angle. So a right angle is 90 degrees. So if you have two right angles, then you get 180 degrees, which is a straight angle. Straight angle is basically a line, two rays. Because remember, an angle consists of two rays. So if they're opposite each other, then that ends up being 180 degrees. So it's not just a straight line. It's really two rays that are attached, which ultimately end up being a straight line. But a straight line would just be like this. You'd have two sides, two arrows, and you might have 2 points to define the straight line. But in this case, we have the two rays that are emanating from the same point. So the answer is two right angles. Okay, the next bunch of questions are true-false questions. So problem 5, a line segment has two endpoints. Okay, so what is a line segment? It's defined by 2 points, which are defined at those points, and a line that connects the two. So this is a line segment. So line segment has two endpoints. That's true. A ray has one endpoint. So again, a ray starts at some point A, and then it goes through some point B, and it has a direction. And it goes on forever, as shown by that. So again, it does have one endpoint. The other end of the ray goes out forever, for infinity. So it is true that a ray has one endpoint. 7, if A and B are distinct points on a line, then ray AB and ray BA represent the same set of points. So let's draw 2 points again, A and B. So ray AB, we use black for that, we just showed it, starts at A, goes through B, whereas ray BA starts at B and goes through A. So here they do share points, but outside they do not share points. So the answer is false. Number 8, if two lines intersect, they lie in the same plane. So we have a line here, and we have a line there that intersect at one point. And so actually two lines you can define a plane by 3 points, or you can define a plane by the intersection of 2 lines. So that is true, that 2 intersecting lines. If they weren't intersecting, then they wouldn't be in the same plane because you wouldn't have a common point. Those are called skew lines. So if this were raised up some, in 3 dimensions, but they never intersected, then they would not be in the same plane. If 2 lines are parallel, they lie in the same plane. So is there a plane that can include 2 parallel lines? Well, yes. In this case, it's the plane that is like the plane of the screen, because I had these. Now, if you had them pointing in other directions, you could also you could create another plane from that. Okay, so the answer is true. Now, if you had skewed lines where this wasn't pointing, into the surface, but it was not, they never intersected, then they wouldn't be in the same plane. But if they're in parallel, then you can kind of connect these 2 ends. If you wanted to sort of connect the 2 ends, and you can see that you could create a plane from that. Number 10, if 2 lines do not intersect, they must be parallel. Well, again, that's the case of skew lines. So in 3 dimensions, if we drew a 3-dimensional representation, which we usually do it like this. So this is like our normal x and y coordinates, and then we have a z coordinate which goes out perpendicular. So it's like the corner of a room. So if you think of it in that sense, like a corner of a room, and you have one line that's going like this, and then you have one lower that's going like this on the other wall. These lines never intersect because these are mutually perpendicular. If I moved it up here, then they would intersect. So those, but down here, again, think about the corner where here's the corner of the room, here's one wall, here's one the other. So these lines never intersect, but they're not parallel. The case of a parallel line would be like that. They would be on the same wall. So these are parallel, and they never intersect. But here's another line that never intersects, but it's not parallel. So if 2 lines do not intersect, they must be parallel. That's false. If 2 lines are parallel, then they don't intersect. That's true. So it's kind of like the converse. The converse is, it's almost like if 2, well, it's an if-then statement, almost like it is an if-then statement. If 2 lines are parallel, then they lie in the same plane. Or actually, we're looking at number 10 right now. If 2 lines do not intersect, then they must be parallel. The converse of that is, if 2 lines are parallel, then they must not intersect. And so the original statement and the converse are not, both of them are not true. So that's an example back from logic days. Number 11, segment AB and segment BA represent the same set of points. Okay, so that is true. Because again, if you have 2 points A and B, the line segment is just all the points between A and B. And so it doesn't matter whether you go from A to B or B to A, you're still covering the same set of points. So that is true. Okay, number 12, there is no angle that is its own complement. Well, that's not true. There is one case. So a complement, remember, is the 2 angles have to add up to each other to be 90. So, you could think of, here's one example. So we'll put an angle in here. But let's say this is 30 degrees. Its complement is 60 degrees. Okay, they're not equal to each other. The one case where that does work out is sorry about that. Just drew in the wrong direction. So here's the X and Y directions, which are again screwed up. So the one case is 45 degrees. So here's a 45-degree angle. 45 is half of 90. So they are the same. This angle's complement is 45, and they are the same. So that that is a false statement, that no angle is its complement. 13. There's no angle that is its own supplement. So again, supplementary angles add up to 180 degrees. So here's our straight line. Here is an angle. Here's another ray. So this angle is something. Let's say again, let's say it's 45 degrees. This angle here, because these two have to add up to 180, has to be 135 degrees. So, but the one case where the supplement is equal to itself is 90 degrees. Okay, so if this angle is 90, this angle here has to be 90 to add up to 180, and they're the same value. So again, that's false. And 14, the origin of the use of the degree as a unit of measure of an angle goes back to Egyptians. Okay, so that says false is the answer. So I need to read the chapter to see why that's not true. And somewhere in here, it's got to explain that. The use of the number 360 goes back to Babylonian culture. That's on page 452. There are several theories regarding why 360 was chosen for the number of degrees. One was that 360 was chosen because it was close to the number of days in the year, and it conveniently divisible by 2, 3, 4, 5, 6, 8, 9, 10, and 12, and other numbers. So that is false because it goes back to Babylonian, which I believe is before Egyptian. Okay, so those are the first bunch of problems.